All right, this one wants us to solve this differential equation again. When you're solving differential equations, rather than using that y prime notation, it's better to use this Leibniz notation because we can then separate out the y's and x's. So here, we'd want to multiply the dx over to the side with the x's. On this one, to get the y over, we're actually going to have to divide here. So that if we divide, this will be 1 over y dy. And so then we want to integrate both sides. On the left side, we know that that 1 over y, the antiderivative, is going to be natural log. And on the other side, antiderivative, go up a power with our reciprocal, and we have a possible constant over here. All right, now to solve this one, we want to try to get y by itself. And this one with just one y, we should be able to, but we need that natural log out of there. To do that, you got to remember that natural log is kind of the same, or is the same as log base e. So if we change this from log form to exponential form, it would say that y is equal to e, and all this stuff would become our exponent. Okay, now to get kind of like our final equation on this one, what we're going to use is kind of a property of exponents here to write that a little bit differently. So think back when we worked on exponents, if we have something like 2 or x squared times x to the third power, we know that that's going to be equal to x to the fifth power. But we could also write that as x squared plus or x to the 2 plus 3 power, because 2 plus 3 is the same as x to the fifth. So what we're going to do on this one, this kind of looks like what we have going with our answer right now. Let's write it in this form. So if you have two things being added in an exponent, you could write it as the same base number with those two powers, and that is equivalent. So going back to the problem we just had, let's write this instead as y equals e to this power times e to this constant. This is the same thing, because if we combine these back together, we'd add those exponents. Well, what we got now is this second one right here. E, remember, is a number. E is kind of like pi. It's equal to a irrational number here. That's 2 point something. So that's just a constant. Its power is a constant. If you got a constant to a constant, that's just another type of constant. And so what you see often in these exponential ones is they will then combine this into just one constant, where it looks like this. So this is usually how you see these ones written out that have exponentials, is they'll take that, they'll separate out that constant into two exponentials, and then the one that's just a constant, they'll use a different constant times that to write your answer. If you now graph this one, the directional field will look something similar to this. You can see over here we have some examples of solutions. For instance, this one that goes through the point 0, 1 right here. That would be like right here on there. It would follow this. It would follow these directional fields, and it would look something like this. So you get that shape to these ones. If you pick something below, same thing. One thing to note here, there is one of those equilibrium solutions here at 0. As you can see, as the limit goes to negative infinity, they all trend to that equilibrium solution. Okay. Let's have you try this one out here. So this one wants you to solve the differential equation located up there. And then once you got that, they want you to use that initial condition right here to find the particular solution to that differential equation. So pause the video, try separating that out, see what you come up with. All right, here's what you should have got here. So we want to separate this. We want to move the dx by multiplying it over there. Let's divide by the y squared, and then you should end up with these two integrals. It's probably easier to think of 1 over y squared as y to the negative 2 in order to find that antiderivative. So use your power rule. You should have got that antiderivative there. 3x squared plus a constant on this side. If we keep going, I'm going to write that y to the negative 1 as 1 over y. Then I multiplied through by that negative to get this positive. And then if we multiply by y and divide by the other side, we end up getting that as our solution with some unknown constant. Now let's use that particular starting location right here to do this. So that's saying that our x here is 1 and our y is 1 over 25. So substitute those two numbers into our solution equation here, solve for c. We're going to get 3. We could cross multiply at this point, and we get this. Add 3 over here and divide by the negative 1, we get negative 28. So now if you take that, put it back in for C, this should be the particular solution that we would get on this one. And that would be the answer to the problem.